Hello everyone, and welcome back to our fourth and final recitation video for this first week. In this video, we'll do a brief introduction to MATLAB and some tools for computations in linear algebra within MATLAB. If you have worked with MATLAB much before, you probably don't need to watch this video as we'll be covering very basic things. But if you don't have much experience in computer science, or you haven't worked in MATLAB before, it's imperative that you start doing so a bit because MATLAB will be not the only, but the primary software that we work with in this course. So let's get started. So first, one of the most basic things in MATLAB that we want to do is define matrices. So you can do this all at once, as is done here. So the syntax in MATLAB for vectors or matrices, we're going to have these square brackets. If you have a space between two numbers, that means two numbers that are adjacent in the same row. And a semicolon means go to the next row. So here, this means we have the top row is 351, the next row is 417, and the third and final row is 231. Note that this matrix was one used in multiple examples from a couple videos ago earlier in the week. So you can check the computations we do here against the computations we did, quote unquote, by hand in those previous videos. So this is one way to define a matrix just all at once. Another way that's common is to define a matrix via columns. So sometimes you'll have a number of vectors of the same length, and you want to just, smush them together into a single matrix. This is how you'd go about it. So here, this is the first column. Here, this is going to be a 3 by 1 vector. So this is just a singular column. Again, the semicolon means we go to a new row. So this has a 3, and then a 4, and then a 2. Similarly, define the second and third columns in this matrix. And then to concatenate these columns side by side, well, recall in the syntax, side by side within a matrix just means you put a space between the entries. Next, you can define a matrix via rows. So here, 3 and then a space, and then a 5 space 1 just means it's going to be a 1 by 3 vector, 1 by 3 matrix. Similarly, define the second and third rows. And now, since rows need to be vertically stacked, we put a semicolon between the rows. Next, in this script, we're going to generate a random 3 by 3 matrix. This is just something very useful in many applications. You want to work with random matrices. So the function there is this function rand. I strongly encourage you to start going through some MATLAB documentation if you're not familiar with MATLAB already. There are many built-in functions in MATLAB for generating random numbers, random integers, many types of objects, which can be quite useful if you need to just generate some random test data to try out various functions or algorithms. So this will show the output of our random matrix. Now, there are a number of operations we can do with matrices. Here, we're multiplying the matrix T we defined with the random matrix we defined. Next, we're multiplying them, but in the reverse order, because recall, matrix addition is commutative, but matrix multiplication is not commutative. So if we swap the order of the two matrices, then the product will be different. Next, we add them, and in this line, what we're doing is scalar multiplication. So if you take a matrix in MATLAB and you multiply it by just a constant value, MATLAB will automatically interpret that as just multiply every single entry in the matrix by said constant value. And lastly, to exponentiate matrices, you just use the normal exponential symbol. Down here, we're going to check a couple things. So first, we're going to define a new random matrix, but now this matrix, instead of being 3 by 3, like T and rand T2, we're going to define as a random 4 by 3 matrix. So now, if we take a 4 by 3 matrix and multiply it by a 3 by 3 matrix, that should be perfectly valid. But if we take a 3 by 3 matrix and multiply it on the right by a 4 by 3 matrix, you should recall from linear algebra that this does not work. You cannot multiply these two matrices in this way because the dimensions are incompatible. And similarly, you can't add two matrices which are not of the right size. Now, rand T is 3 by 3, so if we do that to the third power, then that is going to be fine, but a non-square matrix to the third power, we'll see what it does with that. So let's run. So we scroll up, matrix example, we see T, well, that's what we expect. Then the first column, 3, 4, 2, everything here is what we expect. Again, if you're not familiar, you haven't worked with MATLAB at all, the semicolon at the end of a line means suppress output. So if you have any statement, if you have any statement which has an output in MATLAB and you don't put a semicolon at the end of the line, it will simply print it. So here, that's why it prints T and it prints column 1 because there's no semicolon. It doesn't print column 2 or column 3 because we have the semicolon there. Then T defined by columns. This is again just T, the row, first row, T row. Again, all equivalent ways of defining the same matrix. Now, our random 3 by 3 matrix is as follows. And so note that the default behavior of this random function is to have all of the entries between 0 and 1. But you can modify that as well and see the documentation for how to do so. Next, we go through our test operations. We multiply T by rand T. We get this result. We multiply rand T by T, and we get this result. Note again that these two matrices are clearly different, which again we expect as matrix multiplication is not commutative. Then next we add the two matrices, we get this. Then we multiply T by the constant 3, and you see just every single entry gets multiplied by 3. And lastly, T cubed is going to be very large. We're multiplying T by itself 3 times. Now with error checking, we have rand T2, which is now a 4 by 3 matrix. Rand T2 times T, 4 by 3 times 3 by 3. This is perfectly fine, so we multiplied those two. But then when we tried to multiply 3 by 3 by a 4 by 3, we got this error message. So we simply can't do that. We comment that out. Now let's try and run again. Addition here, a 3 by 3 matrix and a 4 by 3 matrix. Again, incompatible dimensions. We can't do that. And lastly, we try to raise a non-square matrix to the third power, and we can't do that. So you always have to be careful and double check that your code is doing what you want it to do, but MATLAB is also very, very skilled at telling you when you're trying to do something that simply isn't going to work. It's not just going to crash everything, it's going to throw an error. And whenever you're doing just something in linear algebra, the error messages will be very, very helpful the vast majority of the time. So here it's saying incorrect dimensions for raising a matrix to a power, check that the matrix is square. Well, matrix isn't square. There's our problem. Okay, so these are just some basic operations with matrices that we can do in MATLAB. Now, let's see how we can compute kernels and images in MATLAB. So here, we're defining the same matrix T as we've done before. Then we're computing the reduced row echelon form of T, which is a built-in function in MATLAB, just RREF of T. Computing the kernel of T is also something that you can do via a built-in function in MATLAB. And the function in MATLAB is called null. That's another common terminology for the kernel of linear transformation is the null space. So that's why the function is called null here. And we can also compute the column space, or which is equivalent to the image of T. So here, we're going to do so. And let's see what we get. Okay. So here we defined T. Then next we computed the reduced row echelon form of T, which it gives right here, which you can again go back and check from a couple of videos ago. This is the same thing as we computed by hand. Next, we compute the kernel of T, and here with this function null T, and it gives us this, which doesn't look like what we got from a couple videos ago immediately. First, null T isn't telling you the entire kernel of T, it's giving you the basis of the kernel of T. So it's saying that the kernel of T has a single vector as its basis. But you can convince yourself that the linear subspace of R3 spanned by this vector is the same as the linear subspace of the vector we computed by hand. So that's just a one-line quick mental check to do to just verify your understanding of bases. Next, we computed the column space. So here, so we have to use this function sim_t. This is a technical reason inside MATLAB. If you want to know more, you can look up in the documentation. And then call space is, what truly is computing the column space. So this A is what it computes as the column space, and B is what we computed in class by hand as the column space. So these two, now they definitely look a little bit different. And so this is a little bit more involved than the previous short exercise, but these two bases actually span the exact same linear subspaces. So it's a good exercise to just go and verify this, and also something to just be cautious about, if you're doing both computations by hand and computations inside MATLAB, is that MATLAB might give you a result which looks different than what you computed by hand, but that doesn't necessarily mean it actually is different. Okay, and the last thing here was just a I guess quick check on reduced row echelon form. So reduced row echelon form computation is what's underlying all these computations up here, as we saw in class. And so I want to show you how fast reduced row echelon form can be computed in MATLAB. So if we take a random 100 by 100 matrix, it computed the reduced row echelon form in like a 20th of a second. We can crank that up to 1000, and doing so, it now will take a few seconds. So six or so seconds, and it scales upwards, but depending on what you're working with, you can, I won't just sit here waiting in a video, but you can test yourself on a good machine. You can reasonably compute reduced row echelon forms in MATLAB with many tens of thousands of points, as long as you're willing to wait a moment or two. So this is a powerful function that is underlying a lot of linear algebra, including images, column spaces, and kernels. So this was very basic introduction to some of the linear algebra tools that MATLAB has. Again, I encourage you to start looking through MATLAB documentation and becoming a little bit more familiar with the software as we move through the semester. In particular, the project later on in the semester will be primarily completed in MATLAB. So it's important to become familiar with the software and programming language, but we'll try to have a video in MATLAB most weeks in recitation to build up experience with this software over time. And of course, feel free to email me outside of class and/or come to my office hours if you aren't very familiar with MATLAB or maybe needing help or more resources, and I'll be more than happy to talk about it with you then. So that will be all for this week, and I will talk to you next week, where we will be going over the concept of a metric space. So I will talk to you then.